Hello, everyone. Welcome to ILTA Physics Online. Today, we are going to talk about a force that's very familiar in our everyday lives: friction. Friction is a force that opposes the motion of an object. But interestingly, it's actually because of this opposing force that we can create motion in the first place. If there were no friction, we wouldn't be able to walk or run on our own, because our feet would just slip on the ground. So, here's what we'll do today. First, we'll briefly review the normal force, which is closely related to friction. Then we'll look at the two types of friction: static friction and kinetic friction, and clearly understand the difference between them. Finally, from the perspective of friction, we'll use free body diagrams to figure out whether it's more efficient to push or pull an object. Alright, before we get into friction, let's quickly review an important force we studied last time: weight. Last time, we learned that weight is different from mass, which we usually use in daily life to describe how heavy something feels. Mass is an intrinsic property of a material. It's always the same, no matter where the object is or whether it's moving or not. In contrast, weight is the force exerted by a planet, like Earth, pulling an object downward. That means if you change the planet, the same object will have a different weight because the gravitational acceleration is different. The quantitative relationship between an object's mass and its weight is described by Newton's second law. Weight is calculated by multiplying mass by the acceleration due to gravity. On Earth, that acceleration is about 9.8 meters per second squared, and we usually represent weight as W or Wg. Weight can change not only because of different gravitational accelerations, but also depending on the object's motion. This perceived difference is called the apparent weight, which usually appears as a supporting contact force like the normal force or friction. Because gravity acts downward, the apparent weight changes depending on the object's vertical motion. If the object is in equilibrium, meaning it's either at rest or moving at constant velocity, then its apparent weight is the same as its actual weight. As we discussed before, when no net external force acts on an object, its acceleration is zero. So, if we draw the free body diagram, the weight and the normal force are equal in magnitude and opposite in direction. But if an object is accelerating upward, meaning away from Earth, then the net external force is no longer zero. According to Newton's second law, the sum of forces equals ma. So, in that case, the normal force, which represents the apparent weight, becomes greater than the actual weight. The faster the acceleration, the heavier the object feels. You can think of what astronauts experience during a rocket launch. That's a good example of this. On the other hand, if an object accelerates downward toward Earth, then the acceleration is negative or in the minus y direction, depending on how we define our coordinate system. That means the apparent weight, or normal force, becomes less than the actual weight. This is like when you're on a roller coaster and you suddenly drop, you feel lighter for a moment. The relationship between motion and force can be analyzed quantitatively using Newton's second law. But instead of just memorizing formulas for apparent weight, you should always try to draw the free body diagram for each situation and understand it conceptually. Finally, we talked about the weightless condition. Weightlessness doesn't mean there's no gravity. It means the apparent weight becomes zero. When an object is in free fall, moving downward with an acceleration equal to the gravitational acceleration of 9.8 meters per second squared, it experiences zero apparent weight. That's what we call the weightless state. Alright, now let's start today's main topic: friction, a force we can easily observe in daily life. But before we dive into friction itself, let's review the normal force, since the two are closely related. Let's start with the normal force. The normal force is the force that a surface exerts on an object, perpendicular to the surface to support the object. For example, imagine a bag sitting on a table as shown in the diagram below. The bag experiences a downward gravitational force, that's its weight. But it doesn't fall through the table because the surface of the table pushes it upward with an equal and opposite force perpendicular to the surface. That upward push is what we call the normal force. Since the normal force and the weight are equal in magnitude and opposite in direction, the net force is zero. That means the object is in equilibrium, it remains at rest. The normal force automatically adjusts to match the weight acting on the object in the vertical direction, no more, no less. If the normal force were larger than the weight, the object would move upward. If it were smaller, the object would move downward. So, the normal force balances exactly with the object's vertical component of weight. This is actually the same principle we'll see again with static friction in a moment. Now, if the object is on an inclined plane, the situation changes slightly. The normal force equals only the component of the weight perpendicular to the surface. So, you should always remember that weight can be split into two components, one parallel and one perpendicular to the slope. For the same reason, heavier objects exert greater downward force on the surface. That means the normal force acting upward also becomes proportionally larger. The normal force has a very close relationship with friction, which we'll study next. In fact, the two are proportional to each other. This proportional relationship applies to both types of friction, static friction and kinetic friction, which we'll discuss in detail soon. Alright then, let's now start studying friction. Even though friction is something we experience all the time in our daily lives, it's actually not a force that's been perfectly or completely explained in physics. However, through many experiments and observations, we've been able to understand it pretty well. Friction is a force that acts between an object and the surface it's on, and it always acts in the direction opposite to the object's motion. In other words, it's a force that resists motion. But ironically, this resisting force is also what makes motion possible. If you've ever tried walking on a slippery ice rink, where friction is very small, you know how important friction actually is. Without it, you can hardly move at all. Now, take a look at the figure below. If there's a box resting on a surface, and you try to push it to the right, the frictional force will act to the left, opposite the direction you're pushing. If we zoom in on the contact between the box and the surface, we can see that both surfaces are slightly rough or uneven. These tiny irregularities rub against each other, and that's what causes friction. It's basically the result of microscopic bumps and contact points resisting motion. Because friction is a force, it's also a vector quantity. Its magnitude, as we discussed before, is proportional to the normal force, and its direction is always opposite to the motion. Also, friction acts parallel to the surface. If you look at the figure on the right, you'll notice that the heavier an object is, the larger the normal force becomes. That means the contact between the two surfaces becomes tighter, and as a result, the friction also increases. The friction we deal with in physics can be divided into two main types: static friction and kinetic friction. We'll be learning about both of these today. There's also another type called rolling friction, which we'll cover later. Let's start with static friction. Static friction is the force that prevents an object from moving, even when you're trying to make it move. In other words, it's the force between an object and a surface that keeps the object at rest. As we already mentioned, because static friction resists motion, it acts in the opposite direction of the force that's trying to move the object, and it acts parallel to the surface. The key point here is that a force is being applied, but the object hasn't started moving yet. For example, imagine someone pushing a big box to the right, as shown in the figure below, but the box isn't moving. That means static friction is acting on it right now. Let's use a free body diagram to identify all the forces acting on the box. Whenever there's an object on a surface, you should always start by thinking about three main forces. The weight W acting downward, the normal force N acting upward with the same magnitude as the weight, and the friction. Now, since a person is pushing the box to the right with a force F push, the static friction Fs acts to the left, opposing the push. Because the box doesn't move, the forces on both sides are equal in magnitude. If we analyze the forces in the free body diagram, we can see that the box is in equilibrium in both the vertical and horizontal directions. So, the net force is zero, and the object remains at rest. Here's the important point. As long as the object isn't moving, the magnitude of the static friction is exactly equal to the magnitude of the external force that's trying to move it. Just like how the normal force automatically adjusts to match the weight, the static friction automatically adjusts to match the applied force as long as the object stays still. If you gradually increase the force you're applying, the static friction force also increases to match it, up until the object is just about to start moving. That moment, right before motion begins, is when friction reaches its maximum static friction. The maximum static friction can be calculated by multiplying the coefficient of static friction, which is a property of the surfaces, by the normal force. This is why we say that static friction is proportional to the normal force. To summarize this part, when an object is not moving, the static friction acting on it is equal to the external force applied to it, but this value is usually less than the maximum static friction. The maximum static friction, on the other hand, depends only on the properties of the surfaces and the object's weight. It doesn't depend on the external force. And once the applied force becomes greater than this maximum value, the object starts to move. At that moment, the frictional force transitions from static friction to kinetic friction. Make sure you clearly understand the difference between these two. All right, now let's move on to kinetic friction. Kinetic friction is the frictional force that acts when an object is already sliding across a surface. The key difference from static friction is that kinetic friction occurs when the object is in motion, while static friction occurs before it starts moving. Like any frictional force, kinetic friction always acts in the direction opposite to the object's motion, and it acts parallel to the surface. Now, an important thing to note is that the magnitude of kinetic friction remains almost constant, regardless of how fast the object is sliding. When I say almost constant, I mean that in reality, it's not perfectly constant. But in physics problems, we can safely treat it as a constant value. Quantitatively, the kinetic friction can be calculated as the coefficient of kinetic friction multiplied by the normal force. Just like we learned earlier, kinetic friction is proportional to the normal force, just as the maximum static friction was. Now let's consider the situation shown in the figure below. A person is pushing a large box to the right, and the box is moving at a constant velocity. In this case, the free body diagram will look almost the same as the one we drew earlier. There's the downward weight W, the upward normal force N, the applied force F pushed to the right, and the kinetic friction Fk to the left. If the box is moving at a constant speed, that means the object is in equilibrium. The net force acting on it is zero. Therefore, the kinetic friction must be equal in magnitude to the pushing force, just in the opposite direction. Now, let's think about what that really means. The person is pushing the box forward with a certain force, and the box is sliding forward at a constant speed. But the fact that the net force is zero means that the kinetic friction is exactly canceling out the person's push. In other words, there's no extra force left to accelerate the object. In everyday language, this means, I'm working hard to push the box, and the box is definitely moving, but from the box's point of view, the force I apply is completely balanced by friction in the opposite direction. That's why the box just keeps moving at the same speed. It doesn't speed up. This is a great example of how physics explains motion and force in a way that matches our intuition once we understand what's really going on. Finally, one more important point. The coefficient of kinetic friction is usually smaller than the coefficient of static friction. That means it generally takes more force to get an object started from rest than it does to keep it moving once it's already in motion. You've probably noticed this in real life. It's harder to start pushing a heavy box, but once it starts sliding, it gets a lot easier to keep it going. That's exactly what physics predicts. Now, for the last part of today's lesson, let's think about how friction behaves when you push or pull an object, and which method is more efficient. This is a concept that sometimes appears in exam problems too. Imagine a winter sports event where athletes have to slide large blocks of ice across a frozen lake as quickly as possible. Which would be more effective, pushing it from behind or pulling it from the front at an angle? Let's think about this question from the perspective of friction between the ice and the frozen lake surface. First, look at the diagram on the left where the person is pushing the block of ice from behind. If the pushing force is applied downward at an angle, we can draw a free body diagram to figure out how much force is needed. From the standpoint of motion and friction, the easier or more effective method is the one that produces less kinetic friction. Since friction acts in the opposite direction of motion, a smaller friction means that more of your applied force can actually go into moving the object forward. As we've discussed before, whenever an object rests on a surface, there are always three main forces to consider: the weight acting downward, the normal force acting upward, and the frictional force acting parallel to the surface. In the left diagram, the person is pushing with a force F push directed 25 degrees downward from the horizontal. Whenever a force is applied at an angle like this, we can break it down into two components: a horizontal component and a vertical component, as shown by the blue dashed lines. Now, let's focus on the vertical direction of the free body diagram. There are two downward forces acting on the object: the weight of the object and the vertical component of the pushing force. Because both act downward, the normal force from the surface must increase to balance them. And since kinetic friction is proportional to the normal force, a larger normal force means more kinetic friction. So in this case, when you push downward, you actually increase the normal force and therefore the kinetic friction. That makes it harder to move the ice block. Now look at the diagram on the right, where the person is pulling the ice block at an upward angle. We can draw the free body diagram again. The downward weight, the upward normal force, and the leftward kinetic friction are still there. But when we decompose the pulling force F pull into its horizontal and vertical components, notice that the vertical component now points upward. This means that the pulling force is slightly lifting the block, reducing the normal force between the ice and the surface. A smaller normal force means less friction. So in this case, pulling is more efficient than pushing. That's why, from a physics point of view, pulling at an upward angle is the easier and more effective way to move the object. So even in simple everyday actions like pushing or pulling something, physics helps us find the smarter, more efficient way to do it. That's all for today's lecture. Great job, everyone, and I'll see you in the next lesson.